Section 5, there's not that much in Section 5. It's something called the extended real number system. Okay. And what this is basically, how do you add infinity into the real numbers? Okay, so the extended real number system is simply consists of the set of R union these two symbols, negative infinity and positive infinity. Okay, so it's just you take your real numbers and then you throw in these two symbols, negative infinity and positive infinity, and then you make it into an ordered set. Okay, so it is made into an ordered set by one keeping the original order on R. Okay, so if you're comparing any real numbers, your old-fashioned real numbers, then you just use your normal order, and two, defining that for any that x is less than infinity for all x in R, and x is greater than negative infinity for all x in R. Okay, so you say that this is. You need to extend the order. You just say, well, that infinity is bigger than everybody else, and negative infinity is smaller than everybody else. Okay, so that's basically it. There's the real numbers. You throw in these two symbols, and you say that infinity is bigger than everybody, and negative infinity is smaller than everybody. Okay, and that's how you throw infinity into the reals. Okay, so in this sort of new world. Plus infinity is an upper bound for any set in the extended reals. Okay, and another remark: every non-empty subset has a least upper bound. Right? Every non-empty subset has a least upper bound because if S has a finite upper bound, every non-empty subset S has a least upper bound. If a set has a finite upper bound, then your old least upper bound axiom tells you that there is a least upper bound, right? Then the least upper bound axiom for R implies there exists a least upper bound, right? And if there is no finite upper bound, well, then infinity is your least upper bound. Okay? So if S has no finite upper bound, then the supremum of S is just infinity. Okay, any questions so far? Yeah, Edwin.
Can you explain the first
if S has a finite upper bound, right? So if there's some number, right? If there's some m less than infinity, if there exists an m less than infinity, that is an upper bound for S, right? If there's a finite number that is an upper bound, well then we're in that case our set is bounded above as a subset of R, right? We don't even have to think about infinity, right? This set as a subset of R has an upper bound, and so we use the least upper bound axiom from R and say, well, then there's going to be a least upper bound for it. Okay, so anybody who's got a finite upper bound will have a least upper bound. Suppose you don't have a finite upper bound. In that case, infinity is your least upper bound. Okay, so in this world, everybody has a least upper bound. Okay, even sets that are unbounded in your old sense. Okay, so that's what's nice about this. But what's not nice, of course, is that this is not a field. This set, the extended reals, is not a field. Why not? Why isn't it a field? Why isn't it a field? What goes wrong? Yeah.
Is there no inverse for it?
Yeah. I mean, there's in more than one. What kind of inverse?
Multiplicative.
Multiplicative, or maybe even additive, right?
Yeah.
You can't. If you say 1 plus infinity is infinity, right? Should 1 plus infinity be infinity? Maybe. But if you say that, if infinity has an additive inverse, then let's add it on, right? Let's add on the additive inverse, whatever that is, and you see that 1 would equal to 0, right? If infinity had an additive inverse, then you'd run into trouble, right? If infinity had a multiplicative inverse, right, you'd also run into the same trouble, right? 2 times infinity ought to be infinity by how we're thinking, right? So in that case, 2 is equal to 1, right? So throwing in infinity really messes things up. Okay? The only benefit is that you have an upper bound, and sometimes it's useful to consider this set. Okay. Okay. So not a field, but however, it's customary to make the following conventions. Okay, first, we say that x plus infinity is infinity. We say that x minus infinity is negative infinity. One says that x over infinity and x over negative infinity is always 0. So these are for x and r. One generally says that for positive x times infinity is infinity. X times negative infinity is negative infinity. And similarly for the negative numbers, x times infinity will be negative infinity. X times negative infinity will be positive infinity. Okay. So this is one way of putting infinity into the reals. Okay. This is one way of doing it. Okay. And that's basically all there is to this section. Let's introduce this thing. It'll be useful later. You have a bunch of conventions. You know that it's not a field. Blah blah blah. Okay. Just for your amusement, however, let me show you how another way of introducing infinity. So this has nothing to do with anything, but it's just for fun. Okay. So the complex numbers, right? Complex numbers. Maybe some of you know this. Here's the complex numbers, right? It's a plane. Okay. What one does with the complex numbers is you can do something with complex numbers called stereographic projection. Stereographic projection. Okay. So what we just did was we basically said, let's create these things, positive infinity and negative infinity. Okay. With stereographic projection, here's what you do. You take a sphere, and you sit it, a unit sphere, and you sit it on top of the origin here. You sit it on top of the origin, and you say, I'm going to, so here's my North Pole. I'm going to, for every point a plus bi in the complex plane, I'm going to draw a line to the North Pole. Okay? I'm going to draw a line to the North Pole, and I'm going to see where this line intersects my sphere. Okay? I'm going to see where it intersects my sphere. Maybe it intersects it here. Okay? And I'll call that point, if this point is z, I'm going to identify that point as z. Okay? So every point on the complex plane gets identified with a point on the sphere here. This thing is called the Riemann Sphere. Okay. So what happens, say, when I go farther and farther out? If I take guys that are sort of close, if I take guys who are close to the origin, then where do they lie in the sphere? Each in? Sort of in the middle. Yeah, I mean, the closer I get to the origin, what happens? Suppose I get to guys that are close and closer to the origin. How do they appear on the sphere? Suppose I take, I draw a line here, and I take a bunch of guys going in towards the origin. Well, where are they going to tend to on the sphere? They're going to tend towards the origin, right? So maybe they start off around here, but then they start going in like this. Like they start getting in. And if I walk away on that line, far away on that line, then where do I go? I'm going to go higher and higher, right? So I'm basically going to trace out a longitudinal line, right? If I have a straight line here, now as I go farther away, I get a longitudinal line here, right? And you see that as you go farther and farther away, you get closer and closer to this thing on the top, right? But do you ever reach the top? No, you never reach the top, right? Because no matter where you are, you're going to intersect, right? You're going to intersect at some point. You're not going to touch the top. Okay. Well, in complex analysis, you say, okay, the complex plane is mapped onto this sphere, excluding this point. Okay, mapped onto the sphere, excluding this point. And actually, sometimes it's more convenient to work on the sphere than on the complex plane. Okay. And what you do is you say, well, let's close up that hole in the top, and let's just call that thing infinity. Okay, let's close in that hole because there's this hole, right? On the Riemann sphere, there's this hole in the top. What should we call that hole? Let's call it hole infinity because as you head off towards, as your numbers get larger and larger, they're all tending towards this number. So this actually is infinity. Okay. Anyway, just to lure you onwards to complex analysis, which is a course that you could take after this one. Okay. Okay. Yeah, I taught complex analysis last year. It's a pretty cool course.
How many people sign up for that?
How many people signed up for that?
Yeah.
Well, the thing is that I started the course, first I was going to offer Fourier analysis, but nobody wanted to take Fourier analysis. So after everybody had already signed up, I said, well, I guess I'm going to teach complex analysis. So not as many as I would have hoped, but like 8 to 10 students, which was all right, given that everybody had already signed up. Actually, that's not bad at all, given that everybody had signed up. Okay. What? Okay. So, section 6, I'll let you read if you want to. That's an optional section. More important for us will be section 7, the rigorous definition of the limit. Okay, so this is going to be a crucial definition. Okay. So let's start off with a definition. This is a crucial section, crucial ideas in this section. A sequence is a real value function whose domain is of the form n in Z, where n exceeds some m, where m is some fixed integer. Okay, so it's some function, right, on some set of integers bigger than some number. So it could be like from 1 to 3 blah 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 into R. It could be from -2, -1, 0, etc. into R. Right? There's going to be some starting integer, and then you include all integers after that. Yeah.
Is it where m is some fixed integer?
Yeah. Sorry. Where m is some fixed integer. So for example, a of n defined as 1 plus 1 over n to the n, where n lies in the natural numbers. So here's a sequence. Right. Here's another sequence. F of n is -1 to the n. Here's another sequence. S of n is the sum of 1 over n squared from n equals 1 to, the sum of k squared from k equals 1 to n. Okay, so here are a bunch of sequences. You've probably all seen sequences before, right? Everyone seen sequences before? Anyone not seen sequences? You've all seen sequences. Right? So this one, for example, is a simple one, right? It just flips back and forth between -1 and 1, right? This one takes the sum of squares, the sum of the reciprocals of squares from it's like the first term is 1, the second term is 1 plus a fourth, the third is 1 plus a fourth plus a ninth, etc., right? The sum of reciprocals of squares. Okay. One usually notates sequences as a sub n, s sub n, s sub n. So you don't use the function notation. You use this, these sequence notations, and the full sequence, elements of sequences, and the full sequence as something like this. The sequence a sub n as n goes from 1 to infinity. And sometimes people use brackets. Use brackets or brackets. Okay, use one bracket or another kind of bracket. Okay. So, the limit. What do we mean by the limit of a sequence? Okay. So you have, right, for example, a sub n is -1 to the n, right? So the picture is, right, at time 1, you are -1. At time 2, you're 1. At time 3, you're -1. At time 4, you're 1. You're flipping back and forth like this, right? Okay. We don't consider this to be a limit. Okay, we don't consider this sequence to have a limit. Okay. The sequence. We say the sequence doesn't have a limit. Okay, here's another sequence. A sub n is 1 over n. Okay. A sub n is 1 over n. Well, then at time 1, it's 1. At time 2, it's a half. Right? At time 3, it's a third. Right? At time 4, it's a quarter. At time 5, it's a fifth. and so on and so forth, right? And you see that these numbers are closer and closer to 0. And we think of this sequence as having a limit, has a limit, namely 0. S of n being the sum of 1 over k from k equals 1 to n, right? That's going to be 1, 1 plus a half, 1 plus a half plus a third. 1 plus a half plus a third plus a fourth, etc., right? So it starts off at 1, 1 plus a half, 1 plus a half plus a third, right? And so on and so forth, right? What do you think about this sequence? Maybe you know already. What do you think about what's going to happen to this sequence? Does anyone know what happened? Does anyone know what happens to the sequence? Mia, what happens?
Does it go to 2?
No. No. Raleigh?
I think it doesn't have a limit, it diverges.
It actually goes to infinity. Yeah, this one actually goes to infinity. It goes to infinity very slowly, but actually goes to infinity. What about this? What about this one? 1 over k squared. Does anyone know? From k equals 1 to n. So you're taking the squares now, right? 1 plus a 4, 1 plus a 4 plus a 9, etc. Does anyone know what happens to this one? Yeah, Flo.
Go to 1.5.
It doesn't go to 1.5. It goes to something kind of even more interesting than 1.5.
To E?
It doesn't go to e. It actually goes to, it actually converges, it actually ends up at some number, and that number turns out to be pi squared over 6. Okay. But you will not be able to prove that until you take a course in Fourier analysis. Yes, Ichan?
For the sequence like Sn equals the sum of 1 over k, you guys say it goes to infinity, right?
It actually does.
Like it has a limit?
It depends on how you define what you mean by limit. You could say, if you're counting infinity as a limit, you could say its limit is infinity, right? But I think most people would call that divergent. Okay. It's just a matter of wording, though. You could say its limit is infinity. Okay. Okay. In any case, the intuitive idea is that the elements of the sequence should get progressively closer to some number. Right? So generally we say some finite number. Right? If the limit exists. If for a limit to exist, the elements of the sequence should get progressively closer and closer to some number, right? Okay, so this one that we had at the beginning, right? Even though you hit the number infinitely many times, you don't get the elements of the sequence don't get closer to that number, right? No matter how far out you go, the guys jump far away, right? No matter how far out you go, the guys jump far out away. Okay, and so the definition of limit, we have to rule that out. Okay. So here's the definition of limit. Okay, so again, sequence, and L, a real number. We say A sub n converges to L, and write the limit of A sub n is L as n goes to infinity. If given any distance, epsilon, so you want to think of this as some distance, given any distance epsilon, there exists a number n in the naturals such that a sub n minus L is less than epsilon for all n bigger than n. Okay, so here's the picture, right? Here is L. For the limit. Okay, for the limit to be L, means that if somebody says, I'd like everybody to stay, let me say it like this, okay. I think you all agree that in this picture the limit is L, right? You agree that the limit is L for this picture, okay? And you notice what you can do. If I say, can you find me a place where everybody stays between L plus 1 and L minus 1? Can you find me a time past which that happens? You would say, yeah, sure. Past this time, here's some n. Past this time, everybody stays that close to L, right? Now suppose I do it for I take another distance, a half, right? I say, can you find a time past which everybody stays within a half of L? You'd say, oh yeah, looks like if I take this as my time, past this time, everybody stays within a half of L, right? And if I say, okay, what if I take this tiny time, L plus 0.001 and L minus 0.001? Can you find me a time past which everybody stays within that distance of L? You'd say, well, okay, that's harder, but here it is, right? Past this time, all my points satisfy that tolerance, okay? And you see what you can do. No matter what tolerance I give you, there's a time that satisfies that tolerance. There's a time past which that tolerance is satisfied. Okay? I'll say it again. No matter what tolerance I give you, there's a time past which that tolerance is satisfied. That's exactly the statement here. Okay. No matter what tolerance is given, there is a point past which all elements of your sequence are within that tolerance of L, of the limit, of the supposed limit. Okay, so that's really what this block is saying. And so this is the definition of limit. This is the rigorous definition of limit. I don't know what kind of definition you've seen before. Some people will say, well, as you go farther and farther out, you get closer and closer to L. Okay, that's not a mathematical definition. This is the mathematical definition. Okay? And this is what we're going to use to prove things that follow. Okay, sorry to keep you a little late again.